became an RA and had a single the rest of the way. I only had a roommate for one semester.
That's crazy.
Because when you're an RA, you get your own room. So. And your beds are twin long, extra long beds. When you put two twin extra longs together, it's a king. So it kicks out bed. All right, ready? While you snack, which you deserve so much, thank you for everything this year. It's been such a great year. You guys have put up with so much, dealing with so much trouble and adversity, and having to, all of the nonsense that kind of goes along with this year. You have really persevered and impressed me every single day. So thank you for all of your hard work. This is just a little token of my appreciation for everything you've done. Seniors, welcome to your last day of high school. So crazy. And I'm going to teach you one last thing. We're actually going to do some related rates today. Okay, so take out your uniform guided notes. Try to keep the donut dust off them as much as you can.
And it's last day.
Yeah, right. Take all your stuff and burn it in a bonfire tonight.
Oh, that's what I'm doing.
That's the best. It feels so good. Very cleansing. Very cleansing.
I'm gonna go home. It's like we're burning all of our college meal too.
All right, page 259 is where we will start.
Josh has 75 pounds of college meal. Yeah,
weighed it.
I didn't test it from like 2 years ago. So he has everything, and I was like, that's pretty huge.
So okay, now you saw a little bit of it yesterday when we started to look at, if I have some equation that models like some kind of measurement, whether it's a two-dimensional thing with area or a three-dimensional thing with volume, which is really the two that we do. Every now and then, maybe we can get into something linear, but really, like, the easiest thing to do is to draw shapes in 2 or 3 dimensions and kind of imagine them changing, right? Let's, like, pinch and zoom. Like, let's stretch them out. Let's shrink them back down. A three-dimensional shape like that jug of orange juice there. What happens as we pour the orange juice out, or so many different things, right? We can look at how things are changing, because up to this point, math has been so static. It's stuck in time, and we just kind of look at what's happening. Here's a triangle. Let's look at it. Here's a square. Let's look at it. Right? Here's a polynomial. Let's just look at it. Right? But now what we can do, I apologize for the mustache. It's a baseball thing. I know it creeps people out, but thank goodness for math, so I can look like this most of the time. But what we can do is now we can let these shapes change and move and mold, and things are going to happen, and we can fill them with water, or we can let the air leak out, or whatever the case may be. And we can learn about how changing one thing affects everything else, right? The phrase, "a butterfly flaps its wings," right? And everything in the universe changes. You know what I mean? So that's the kind of thing that we can look at. So here we go. The easiest thing to do is to kind of envision, like close your eyes or draw a little picture of what's happening, and watch things change and see if we can get on the same page. And what they do, which is really nice, for the first 4 practice ones, and I don't know that we'll need to do this with every single one that we do, is they give us a really nice layout of how to deal with related rate problems when you're new to them. Once you get comfortable with them, like even by the end of today, I don't think you're going to sit here and do 1, 2, 3, 4, 5, and 6. Eventually, you just say, okay, I know what I got to do. I've got a nice shape. I can come up with some sort of equation that I can differentiate and then plug some stuff in. Because what they're going to do is they're going to give us a scenario. They're going to give us lots of information, everything we need except one. And that's the thing that we'll solve. Okay? So air is leaking out of an inflated balloon in the shape of a sphere at a rate of 230 pi cubic centimeters per minute. What dimension are we in if it's cubic centimeters? The third dimension. Okay, and so we're going to need at least a third dimensional equation in order to do this. Okay. At the instant when the radius is 4 centimeters, so that's when we'll stop. We'll kind of pause time and see what's happening there. What is the rate of change of the radius? Okay, so we're going to let air kind of seep out of this spherical balloon. We're going to watch it happen, and then at the exact moment when the radius of that balloon is down to 4 centimeters, we want to figure out how fast is the radius changing while it happens. Okay, and a good thing to do to make sure you've got what you need is to figure out, okay, what are the variables? What's happening in this scenario? Is it like a linear thing? Is it a rate of change? Can we figure out what we've got? Okay. Then we'll decide if any of those variables are going to remain constant. This is a balloon shrinking, so I don't think so. Right? Everything's going to change as that happens. But sometimes if we do have a variable that does stay constant, it'll help us with our differentiation because that can be treated like a constant. Like 3 is a constant. Well, maybe R or H or whatever is a constant too, and it just makes the derivative part a little bit easier. We'll figure out what we've got. Okay, like, all right, here are my variables. What is it? Right? Here's my rate. What is it? And then we'll create an equation that we can use. So what do you think? Take a look back. Let's go back here slowly. What do we have? Air is leaking out of an inflated balloon at 230 pi cubic centimeters per minute. What is that? A three-dimensional measurement. And we have a rate that goes with it. How do we measure space in 3 dimensions? What's that called? Volume. Volume. 3 dimensions.
Geometry.
True. And let's get more specific and let's talk about a 3-dimensional space. Geometry is the study of shapes. That's good. We're on to something. A sphere is a shape. You're not wrong. Man, this is the last day. Okay. But what they gave us was not like, here's the volume of this sphere. Here's the rate at which the volume is changing with respect to time. How could we say that? The rate at which the volume is changing with respect to time. How could we write that as simply as we could? Using, like, calculus. The rate. Yeah, dy dx, but let's use better letters. Dy dx is the rate of change. dv, the rate at which volume changes with respect to time. dv dt. That's one of them.
Okay, guys. I'll see you.
Okay, so there's one of our variables. It's actually a rate. A variable is part of what we got. Okay, so there's one. There it is, 230. And it's leaking out. So we'll kind of keep that in mind once we go. Okay, I'm going to switch colors just to see. What else do we have? So that's the first sentence. Cool.
Radius.
Radius. Okay, sweet. R. There it is. The radius is going to be 4 centimeters when we pause time there for a second. Okay.
Rate at which the radius changes.
Okay, now we have one more rate of change, and that's the one that we're actually trying to figure out. That one we don't know, but how could we say the rate of change for the radius? It was the volume when we did dv dt. Now it's the rate of change for the radius. dr dt. Nice. Perfect. Okay, and so those are the 3 pieces to this puzzle. Okay. Of course, with dr dt being the one that we're going to look for. They gave us dv dt. They gave us r. We're good. We have 3 pieces. Only one of them's missing, which means we only need one equation to solve. And in this case, because it's a sphere shrinking, we don't have any constants for those variables. Now, yes, the rate is constant. That's not part of our original equation. Okay, the radius at that moment will stop changing, but you don't want to like look at the picture of what's happening. You want to look at the video of what's happening. You want time to pass and see what is changing as all of this happens. And if something isn't, then we can treat that like a constant. But in this case, we have a lot of things moving. We got a lot of moving parts here. And so what we want to figure out, okay, what is dv dt? What is r? What is, I'll do this. What are these 3, dr dt, sorry. Ooh. dr dt.
That was the most related.
Okay, what is dv dt? Did they give it to us? 230, yeah, but think about this. Air is leaking out. The rate of change, right? The volume itself, whether it's increasing or decreasing, is going to change the sign of our derivative. Remember, the derivative is rate of change, right? It's the slope of a tangent line, sure, but really it's a rate of change for what we're dealing with. If something is increasing, that rate is positive, right? The derivative is positive when things are increasing. Here, the derivative is negative. Negative 230. If you want to write the cubic centimeter part, as part of your work, fine. I like to keep units out of my formula until the end, and then I will just decide, okay, is it linear? Is it dimension 1, dimension 2, or dimension 3? If it's a first dimensional straight line, then I don't need like square this or cubic this. It's an area, cool, square feet, square inches, square whatever. If it's 3-dimensional, cubic. Okay, cool. What's the radius? 4. 4 exactly, right? We're gonna pause time right here, right now. And then what's dr dt? That's the question, right? That's what we're trying to figure out. And if you can figure out, here's what I got, here's what I need, all we need now is a formula that eventually, once we differentiate, we will have all 3 of those pieces in there. And we can solve for the thing that's missing. And it usually is just some geometric formula that has to do with the shape of the object. And it could be an area, it could be trigonometric, if it's a triangle. What shape do we have? Shape of a sphere, okay? 3-dimensional shape. We want to measure some space in 3 dimensions. What do we need? How do we measure space in 3 dimensions? Volume. What we're gonna need, and I'm gonna erase some stuff here just so I can move down. What we need is geometry. There it is, A+ for yo. We need some volume measure. And again, this equation is directly related to the shape that you give. Okay, sphere, volume of a sphere. Area, area of a circle, or area of a square, or area of a rectangle, whatever you're looking at. Or maybe it's some trig relationship because you're looking at sides and angles. Okay, what is the volume of a sphere? And if you need to peek back a page before to find it,
4/3.
4/3 pi r cubed.
I need that.
We are in 3 dimensions, so we need a variable of degree 3. Now, maybe you've got 2 different variables. Okay, well, I need their exponents to add up to 3 or whatever. Okay, now, and I'm going to do it I'm just going to work my way down here. Now I'm going to implicitly differentiate with respect to time. Okay, and that's always the plan. And maybe 2, 3, 4 problems from now, you just start right there. You say, okay, here's the shape that I've got. I am just going to write that equation down. I'll differentiate, and then I'll figure out what pieces I have. You don't necessarily have to go 1, 2, 3, 4, 5, 6 once you get comfortable with it. So let's do it. Let's find ddt to the left. Let's find ddt to the right. Oh, cubed. Sorry. 4/3 pi r cubed. And let's figure out what we get once that all happens. The nice part about related rates is if you can get comfortable with the process, you see how similar all of these are going to be. And for me, I'll never ask you to memorize the geometric formulas. You just have to, find it on a list somewhere, look it up, but you have to know how to differentiate implicitly because we're going to always do it with respect to time. And none of these formulas are ever going to have time in them. They'll have radius or height or length or width or whatever. Okay, so let's do it. Left side, the derivative of volume with respect to time. What's the best way, you think, maybe to write that left-hand side, the derivative of volume with respect to time? dv dt. Yeah, absolutely. That's what we got. dv dt. Cool, there's my left side. Now, if that was v squared for whatever reason, and I don't think it never would be, but 2 drops in front, v to the first, right? It's power rule, and then a dv dt at the end. But this is just v to the first. It's linear, so the derivative of something linear is just the slope of that, and there it is, dv dt. Okay, now the right side. The derivative of all of that with respect to time. How many variables are in there on that whole right side? 4/3 pi r cubed. 1, just r, right? And so when we differentiate that right-hand side, I don't need the product rule, I don't need chain rule or quotient rule or anything like that. I just need to pull the constants out and really kind of focus on the r to the third part, right? 4/3 pi times, okay, now we just do the derivative of r cubed. And we treat r cubed the way we would treat any derivative. It's just that I know the variables don't match r and t, okay, so we'll have a dr dt again. Right, just like we always had a dy dx at the end, same thing here. The variables don't match, we just need that differential. So what is the derivative of r to the third? 3r squared. Drop the 3 in front, decrease the power by 1. Simple power. We just need something after that because the variables don't match. Kind of a chain rule kind of thing, right? If it's the derivative of r that we were taking with respect to time, what do I need attached at the end here? dr dt. Beautiful. There's our differential equation that has all of the pieces that we know and only one missing piece. The missing piece, though, is over here, right? Kind of attached to some stuff. So let's clean it up a little bit. Let's make it look at least a little bit nicer before we do anything else. dv dt. Do you see anything on the right-hand side that we can kind of put together, make it look a little prettier? Get rid of 4/3 and 3. What's 4/3 times 3? 4 pi r squared dr dt. Now, dv dt, r, dr dt, those are our 3 missing pieces. We know 2 of them, so we can solve this directly. For me, even though we're solving for dr dt, and you could, like, let's divide both sides by 4 pi r squared and, like, isolate what you want and then plug stuff in. Sometimes that can be a little bit tricky because this is written as a fraction, but this is what negative 230 pi, right? It's not a fraction once I plug stuff in. I'm of the belief that once you simplify your equation a little bit, I'm going to plug my numbers in now. I'm going to evaluate now, simplify, and then solve. I find that a little bit easier than like solving for dr dt and then plugging stuff in and then simplify. Because things might work out a little bit nicer, plus I avoid some trouble along the way. So I'm going to drop in my numbers that I know, simplify, and then solve. So what's dv dt negative 1? 230 pi. If you want to put cubic centimeters in your equation, you can, but those units can get a little messy to deal with. I'm just going to figure them out at the end. Okay, 4 pi, do we know r? 4, okay, so 4 squared. Do we know dr dt? No. That's what we want, so I'm just going to leave it, dr dt. Okay, let's make the right side a little nicer. 4 pi times 4 squared. So it's really 4 times 4 squared that I have to do, which is 4 to the third, 64. 64 pi dr dt. Nice. So there's like the evaluating and simplifying step in my mind that I find way easier than like moving stuff around while you still have all of your differential terms in there. dv dt, the dr dt. I don't want to put stuff in and move them around until things are simple. Okay, now let's solve for dr dt. How do we get dr dt by itself? Divide by whatever's attached. 64 pi, 64 pi. Those are gone. The pi's are gone, so that's nice. I'm just going to come over here. You got more space than I do. So dr dt is by itself. I'm just going to slide that back over to the left because it just makes my brain happy. Negative something. Negative what? Is that perfect? Does 64 go evenly into 230? No. Can we simplify it? They're at least both even. So we can divide everything by 2. Can we do any more than that? Like this is definitely, in my mind, I drop that in the calculator. If the decimal is really nice, I can use that. If the decimal has, like, it keeps going, because maybe it's rational but just ugly, I'm going to write the best version of that fraction. Now, it's calculus, it's Calc AB. We can always round to 3 decimals and be okay. I like to have the right answer. What is the best version of 230 over 64? Yeah, that's it, 115 over 32. And if you're not sure how to do that, drop it in the calculator, and then math, arrow, frac, and it'll change it back. Okay, negative 115 over 32, what? What do we have, right? We have a rate with respect to time. So we're going to want like a miles per hour, feet per second, cubic centimeters per minute, whatever we've got. We want to have a distance measurement in the right dimension over whatever time measurement we've been using. So radius, a straight line. What dimension are we in if we just have a line? No space inside the measure. The first dimension. Okay? First dimension, straight lines. Second dimension, area. Anything area. Okay, measurable area. Third dimension, volume. What size are we dealing with? Feet, inches, centimeters, what? Centimeters? Okay. So centimeters per, what's our time? Is it minutes? Minutes. And there we go. This is how fast the radius is changing if all of those other things are true. And of course, change the point where you stop, right? And how quickly the radius changes is going to be different once we do that. Change how fast we're letting the air out. It's going to change how fast the radius is changing. Change how fast the radius is changing. That's related rates. Okay, that's what we're going to do. We're going to find a nice little formula. We're going to differentiate both sides. We'll plug in what we know, solve for what we don't, and just make sure our units make sense. And so seriously, like for me, and this is why I like erase stuff and started right here, I think a problem or two from now, this is what your work starts and looks like. You don't need all of that. Here's what I know. Here, you know, it's all in the problem waiting for you. For me, this is my related rates beginning. I find the formula that I need, I differentiate, I drop in my numbers, simplify. Okay, but their process is nice for us just getting started. And so we'll do it again. Go ahead, turn the page. Let's do at least one more, maybe two if we can. This scenario just makes me feel so at peace. A stone is dropped into a calm body of water, causing ripples in the form of concentric circles. What is a concentric circle? So what does concentric circles look like? Nice. Rather do that again. Yep, right. It's just they have the same center and out they come. And you can kind of picture that happening, right? You drop a stone into the water, and if this was like, if we could like take like 5 pictures and like lay them over each other, right? The ripple would just kind of continue to go out like that. So that's kind of the shape that we're dealing with, but we only care about one of them. Okay, because we want to do one thing at a time. The radius of the outermost ripple, okay, is increasing at a rate of 1 foot per second. When the radius is 4 feet, how is the area of the water changing? So let's go slow, at least for one more time. Let's do number 1. Let's take a look at what we've got and see if we can identify variables and see if any of them are going to stay the same so our differentiation gets a little bit easier. A stone, and I read the problem and then I say, okay, now I go back through it. Let me see what I've got. So there's the picture in my mind. Okay, the radius of the outer ripple is increasing at a rate of. What is that? The radius is changing. It's a rate, dr dt. Well done. So there's one. Okay, that's this one. The radius is increasing at a rate. So I know we're talking about a rate, so I need a differential to do it. When the radius is just r, good. And then last one, at what rate is the total area of something changing? dA dt, nice, right? We had volume changing, so that was dV dt. Now we've got area dA dt. And this is kind of where I close my eyes and I say, okay, if those are the 3 things that I care about, sometimes there's 2 or 3 or 4 pieces, excuse me. As that circle, like I see, it's like I close my eyes and I kind of like envision the circle opening up. Is anything going to stay the same? Is the radius really, like, is the radius going to stay the same? Oh, of course not. It's changing, right? And so for me, in my mind, no, nothing is changing. The thing that I think is going to help you see when things will stay the same, imagine this picture. Okay, imagine like filling a cylinder with water. Right, the water is going in. Is the radius of the cylinder changing as I add water to it? No, but that's still going to be part of my volume equation or my area equation or whatever. Okay, the height sure will, right? That measurement right there is going to change whether I fill it up or I poke a hole in the bottom. and let the water spill out, that'll decide whether dH dt is increasing or decreasing, right? Positive. But in this case, nope, we're good to go. I think we've got what we need. We know what we want. We want to find that, the rate at which the area is changing. And so I think we're comfortable enough. If you're ready, let's just find ourselves an equation, plug in the numbers we know, solve for what we know. What shape are we dealing with? Last one was a sphere, so we did bottom of the sphere. What shape are we looking at? Circle. Right, a bunch of them, kind of working out, but we really just care about the one, the outermost one. What dimension are we in if we're looking at a circle? Second dimension, so I need a second dimension measurement equation. How do we measure things in the second dimension? Area. What shape are we dealing with? Circle. What's the area of a circle? Pi. Good job. There's our starting equation. If you can land there with the right equation, the rest of this kind of takes care of itself. Let's implicitly differentiate both sides with respect to time. Plug in what we know, solve for what we don't. Last time we had to solve and move stuff around. Let's see what happens here. Let's do ddt to the left, ddt to the right. Let's see how it goes. So what do you think? Left-hand side here. The derivative of area with respect to time. How can we write that? Good. dA dt. Okay, now right-hand side. We have a pi constant, so I can just, okay, I'm going to pull that out and kind of just worry about the rest. You don't have to, right? But it is kind of nice to get used to kind of pulling the constants out and just dealing with the other part of the derivative. You'll see the further up we go, the more useful that gets. Okay, now I need the derivative of r squared with respect to time. 2r for sure, because I'm going to drop the 2 in front. I'm going to decrease the power by 1. But the variables don't match, so I need something after that. Very good. Little dr. It's all connected by multiplication. The dots, if you want, totally up to you. Just kind of keeps things in my mind separate. Pulled up the pi, did my derivative, have my differential after. And you can move stuff around and simplify it now if you want. So totally up to you. Or we can just dive into it. It's all correct. There's really nothing I can put together. Really, I'd just be reordering it to like 2 pi r dr dt, which isn't really doing a whole lot to make things simpler. So let's just jump in. So what's dA dt? They give that to us? Well, that's what we want. Try to solve for that. Oh, yay, look, it's already alone on one side. That's going to make this problem even easier than the last one. I don't have to move things around too much. It's already solved for. So really all I have to do is plug in what I know. Pi is pi. 2 is 2. What's r? Cool. And what's dr dt? And because the dr dt is increasing, it's positive 1. If we were like letting the circles get smaller, it would be negative. Okay, so dA dt, pi times 2 times 4 times 1, 8 pi. Now we just think about the units. Now, you could like include the units as you go. Like r is in feet, right? And dr dt was in feet per second. Is that what it was? What do you think? Feet times feet per second. Feet times feet. Square feet. What dimension are we in? If we're talking about area, there's the square. Okay, so if you want, you can like let the units get you there. You just have to be careful because if you're taking a cubic foot and dividing by feet per second, well, now it becomes square feet per second or whatever it might be. But there we go. Now here's the thing. Either is acceptable, square feet or feet squared. Okay? Conventionally though, the metric system is the one that uses the exponents. Okay, centimeters versus centimeters squared versus centimeters cubed. The imperial measurement system here in the good old US of A, we put the measurement size first, feet, sorry, square feet. I don't, that just looks so bad, I can't deal with it, sorry. Usually we do the size, like what dimension we're in, square feet. But feet square is fine. If you want to put FT and then a little 2 on top, that's cool. Okay, this is conventionally the way it's done. And there you go. Again, like this is where my work would begin. Once you get comfortable with it, you say, okay, what's my equation? Differentiate, plug them in. That's all. Cool. Larry, we got time. Let's do one more. Let's do one more. Tomorrow, in my absence, you'll just try some more on your own or with other people. It's cool. And Felix should be in here. So now he's taken lots of calculus, but he's never taught it. So I'll probably sit down with him and remind him about how related rates work, so you can ask him for help should you need it. And I will let you know which ones to do, and you'll just put that up on Canvas. We'll call it classwork 4.1, I guess, since it's the first one. When you're done, get as much done as you can. Okay. Now, I didn't draw out the sphere for the balloon. Here's how you do it, though. Give yourself a third dimension by going in and out. And pictures can really help as you're dealing with things. Right, there's my sphere. You saw me draw the concentric circles. I think that that can be really helpful. Anytime you have these kind of things, draw a picture if you find it to be helpful. Okay, what we've got now is something in the shape of a cylinder. What is a cylinder?
Circle with the bottom.
Circle with the bottom.
Why can't I think of a cylinder?
Like, what is this? Like, yeah, circle with a bottom. Tube.
2 circles and a rectangle.
2 circles, kind of wrapped like, you know, so you got like a circle on one side and then 2 circles in a rectangle.
Everyone just forgets.
Like a Pringles can. A can of something. That's what you're looking at. Okay? And so if it's helpful to draw something in 3 dimensions so you can see it, go for it. Okay? It's up to you. I just like to draw a picture so I know what I'm looking at. Okay, water is leaking out. All right, so you got some water sitting here. Probably draw it like this. Right? So we got some water in here. Okay, and it is leaking out. Somebody poked a hole in the bottom. I don't know. Maybe they're trying to water their plants, but not too fast. At a rate of 3 cubic feet per second, the radius of the tank is 4 feet. At what rate is the depth? Oh, depth. How about height? Height of the water changing at any instance during the week. The reason I changed depth to height is because when I'm thinking about measuring, we usually use H for height and that's D for depth. So, but whatever works for you. Okay. One last time, let's see what we got, see what we're working with, and then we'll get after it. So what do we have? The water is leaking out at 3 cubic feet per second. What is that? It's a rate.
3.
dV, dt, and it's leaking out. I'm just going to write down what it is. 3 cubic feet per second. Negative. Good. We are losing water. Negative. Again, you want to put cubic feet or feet cubed. That's up to you. Okay. Radius of the tank is 4 feet. Okay, cool. So that's easy. So R is 4. So this right here, that measurement right there is 4. The radius of the cylinder. Okay. And then we're trying to figure out what the rate of the height is doing. So like this measurement right here as the water leaks out. What do you think? Is water leaking out? Is that height going to increase or decrease?
Decrease.
So do we think our answer eventually will be positive or negative? So that'll be good for us, right? To kind of get a sense of what sign we should have. And so that's what we want. We want to figure out DHT. That's what I don't know. Okay, cool. Are any of those things going to stay the same as the water leaks out? The radius of that cylinder. Because once I like narrow in on what actually will stay constant, r is a variable. And so far we keep having these, you know, the r and the drdt. Do you see a drdt up there? Well, then we don't have something changing. And if you had differentiated, and we'll see why, and you had a drdt and a dhdt, because maybe you didn't notice, and that's okay, right? You're just making your life a little bit harder. If they don't give it to you because it's staying constant, what is drdt, the rate at which the radius is changing if it's not changing? Zero. And so if you had done all of this work and you end up like product rule and doing all these things and you get a drdt, it's 0 because it's not changing, and that whole term is going to disappear anyway. Okay, so there's our setup. We have identified them. We've given it, like, we figured out what they are, right? We know what we want and we know what's constant. So now it's time, and this is where my work certainly would begin. I'm going to leave our little picture up there though, to figure out what dH dt is. And so we need something that has dv dt, r, and dH dt in there. What formula do you think we could use, given the fact that we drew our little three-dimensional picture there? You're in the third dimension, yeah.
Wouldn't it just be volume equals area of a circle times height?
Good. Volume of any cylinder is the area of the base times the height. So since it's a circle, we use pi r squared. If it's a square or a rectangle or a triangle or whatever it is, area of the base times the height. So that's pi r, oops, forgot an r. Said it, I didn't do it. Pi r squared h. And when we kind of keep going here, you'll see why knowing that r is constant is going to save us some trouble. What do we do now? We have our little formula. What should we do with it? Differentiate. Okay, let's find ddt of both sides. I like to write this step in blue because I don't know, it slows me down a little bit. Sometimes in math, I try to go too fast, and that's when I make mistakes. So writing it like that will allow me to kind of deal with the right side, deal with the left side separately. Let's see. So what's the left side? dv dt. Okay, now, before we differentiate the right side, like we had for the last two problems, let's pull out the constants and differentiate the variables. So give me a constant on the right-hand side. Pi. Is anything else constant?
Yeah, r squared.
R squared. Okay. If you don't notice that, you didn't like think about what's constant in the situation, you would have had to do the product. Right? R squared and h, if you thought they were both variables, you'd have to do u dv plus v du. Eventually you'd get drdt. That would be 0. That whole term would disappear. And we just end up with this one anyway. So now we're just really finding the derivative with respect to time of h. Well, just like v is linear to v to the first, this is h to the first. Let's treat them just the same. If the derivative of, with respect to time of v is just dv dt, what's the derivative with respect to time of h? dh dt. Seniors killing it on the last day. I love it. Now, there would have been like a 2rh drdt term. If you left it as a variable, the drdt would have been 0 and the whole thing goes away. So now, life's a whole lot easier. Long story short, if you miss it, you'll still get it right. But you're going to have a missing piece in there that isn't in the problem. You just have to like think more. It takes more critical thinking. Okay, what we're trying to solve for this, right? dH dt? Okay. So do we know dv dt? What's that? -3. Okay. Do we know r? The 4 again? Okay. And this is what we're solving for. So like I said, I like to like plug stuff in, right? I like to substitute, evaluate, simplify, and then solve. The order though is kind of up to you. Like you could have like divided both sides by pi r squared and then plug stuff in. That's cool. Whatever you're into, whatever works for you. I like this way. 16 pi. dH dt. Okay. And so how should we solve for DHGT? Everything's plugged in, simplified as much as I can. Now let's start solving. -3 equals 16 pi DHGT. Last step here. What do you think?
Divide by 16 pi.
Sounds good. -3 over 16. If anything there could have been simplified, I would have. Right, if that was like 15 pi, then I would just simplify the fraction. No need to, and really no way to rationalize that denominator. So we're good, just leave it like that. Now we just have to think about units. What dimension are we in, and what measurement system are we using? dH, dt. H, height, straight line, what dimension? Volume is 3, area is 2, straight lines are 1. Okay. You know what dimension we are in if I just do this? A single point of length 0. What dimension are you in? I'll let you think about that.
Are you not going to tell us?
And I'll ask a second question. What's the fourth dimension?
What's lighting?
What's the
I'll do you one better.
What dimension is adding?
What is it?
Adding time to all of it, so you have like.
Move the third dimension through time, and you're in the fourth dimension. So we live in the third dimension, but you experience life in the fourth. The third dimension moving through space. The fourth dimension is the only dimension that is not spatial. First dimension is a measurement of space. Second dimension, measurement of space. Third dimension, measurement of space. Fourth dimension is time. The fifth, sixth, seventh, eighth, ninth, 10th, and 11th dimension, those are all spatial. And yes, we believe that there are at least 11 dimensions. And there is the theory of infinite dimensions.
Yeah,
Parallel universes, things.
Wow.
So first dimension, are we in feet, inches, centimeters? What do we got? Feet, right? Feet per second, minute, hour? Second. Voila. And look, it's negative, yay. That's how fast the height is.
What is a dot?
Huh?
What is a dot? A zero?
Because I can't measure it. If I can't measure it, it's not dimensional. The first dimension I can measure by like measuring how far it goes, right? Second dimension, I measure the space inside. Third dimension, I measure the volume inside. How do we measure the fourth dimension, the third dimension moving through space? With rates and calculus. Yeah.
Sorry, I forgot to give this to you yesterday.
Ah, yes, thank you, sir. Appreciate it. I'll get that graded and back to you next week.
Thank you.
You're welcome. Thank you.
Mr. Rosengren.
Top yourself off on your way out if you want. Trash any garbage if you have some.
If I switch the lids, would you want this?
Switch the lids.
Yeah, so like take the lid off and we grab a new one.
I'll see you at graduation. Yeah, this is not goodbye. It's just see you later.
So like if I take this off and then get a new lid, so you don't have to drink off the
Recycle.
lid, but
Recycle.
it's full.
Oh, the coffee is fine.
Yeah,
Do I want the coffee?
if I switch the
No,
lids.
it's probably better if we don't. So you can leave the cup and I'll dispose of it for you. I'll just like pour it down the sink. Yeah, so leave it right there. Bye, everybody. Thank you. I'll see you Monday, seniors. I'll see you at graduation. Now, seniors, speaking of you guys, since you're all here, some stuff is going to come out either later this week or early next week about graduation. There's going to be a rehearsal video. Like, there'll be a virtual rehearsal. We're not actually going to go to Echo Park. But it should be really easy and simple to follow. But you want to watch it so you know what it's going to be like a week from 2 weeks from today? 2 weeks from today. So I'm guessing it'll come out like next week. Like, here's how we stand, here's how we walk, here's where you're gonna sit. Everybody will have a section and either a front or back of that section, but no specific seats, except honor grads. Okay, so 4.0 or higher. Okay, you will be sitting in the front row of your section. Doesn't matter where, but just something. Okay, so all that info will come out next week. Anderson and I are head of the graduation committee, so I know all this stuff. So if you have questions over the next couple of weeks or whatever,
Okay.
just
I
come
feel
to
like you're ahead of every committee this program.
Well, they try to. I have to say no to some things because I can't do it.
Thank you, Mr. Rosen.
Love you guys. Thank you so much for being here.
Do you want to see the art inside of it?
Yeah. I didn't know there was art inside.
Yeah, this is like.
Sneaky, sneaky.
That's funny. That's important. Thank you.
Who made all this?
Me?
You?
Yeah, my cherry blossom.
Cool.
And then there's this pencil.
Nice. I like the shading there.
Thank you.
Shading's good.
Voices.
Shading is what makes it three-dimensional.
She's what makes it
It really does. I love the shading.
And then this is Persephone wallflower.
Uh-huh.
And
Mhm.
then this.
Very nice.
Yeah. This is all my last art projects. I did this all on like Sunday night.
Really?
Yeah, I know.
Is
She's
it
like,
for drawing and painting?
yeah, I
Cool.
love that class.
Me too. That
Yeah.
was what I did in high school. That was like my
Yeah.
main art was drawing and painting because I wasn't great at sculpture.
Oh no, I suck at
I wasn't
that.
great at ceramics, and we didn't have, because I was in such a small high school, we didn't have as many options. We didn't have jewelry and all that kind of stuff. It
Oh
was just
yeah.
like, you did art, you came to art class, you did
Yeah,
whatever
I
we
remember
did.
it, yeah.
And so I actually took AP Advanced Open Studio, which was,
Oh.
and so I took that for 2 semesters. And so like first semesters, you worked on a bunch of little projects
Mhm.
and then submitted that, so you just kind of made a portfolio. But then second semester was you did one piece of artwork all semester long.
Oh.
And for me, it was this 3x5 painting,
Oh
yeah,
wow.
which I still have in my basement.
Wow, that just
Pretty
seems
cool.
really fun. I wish and that was in high school?
Yep. We had like the back of the art room was just for seniors in Advanced Open Studio.
I
So it was like
wish we
7
had
of us
that.
back there. We
Oh my
like
God.
became close. I even drew one of my friends from class. She's in my painting. So it's this landscape, and there's like a house that's burned down, and she's like sitting there with her legs crossed like this, like
That's
just like
so cool.
surveying the fire. It was cool.
Wow, I
I'm not
wish
the
we had
greatest
that.
artist, but it was pretty fun.
Oh no, I just do it for fun, but I'm like, oh my goodness,
Yep.
that's so cool. I wish
Yep.
they had that.
I know, right?
Thank you.
You're welcome. Have a good one. See ya.